Today we are going to talk about the surface tension. Okay, now let's understand what is surface tension. So now there are two kinds of intermolecular forces, the cohesive force and adhesive force. So what is the cohesive force? It is the intermolecular force between the molecules of same types. Okay, that is molecules of same substance, you can say same material. Okay, and adhesive force is intermolecular force between the molecules of different substances. Okay, cohesive force, the intermolecular force between the molecules of same kind of substance, okay, same substance, and adhesive force is the intermolecular force between the molecules of different substances. There is a certain range up to which this intermolecular force acts, so that is known as the range of molecular attraction. Okay, so what is range of molecular attraction? It is the distance between two molecules up to which the molecular forces can act, right? And this range is of the order of 10 raised to minus 9 meters, that is 1 nanometer. Okay, so molecular forces act up to the range of 1 nanometer. Okay, so then now if you consider any molecule, and if you take this molecule, suppose you take this molecule and you take a radius equal to the range of molecular attraction and draw a sphere, then that sphere is known as sphere of influence. So what is meaning of the sphere? So if you consider any molecule, then it will get attracted from the molecules in the surrounding region which come within this sphere. Okay, this is known as sphere of influence. So it gets influenced by the molecules within this sphere, right? So now consider this molecule which is well inside the liquid. So this is some water in a container and this molecule A, for an example. Now draw a sphere, the sphere of influence for this molecule. So now if you consider this molecule, it gets attracted from this side, it gets attracted from this side, this side, this side. That means it gets attracted equally from all directions. What will be the net force acting on it? Because this molecule A gets attracted equally from all directions, therefore the net force acting on this molecule would be equal to 0. Now consider the molecule C, which is at the top layer, okay, top layer of this liquid, that is water. Now if you draw a sphere of influence for this one, then half of the sphere is inside of the liquid, half of the sphere is outside of liquid, that means it is in air. Okay, so there are very few air molecules because density of air is very low, right? So then this molecule gets attracted by other liquid molecules. So if you take water, it gets attracted by other water molecules, okay, and that net force acting on it will be downwards, right? Simply because there are more number of molecules, you can say, in this half sphere or hemisphere, okay, compared to that of this part, because air is, first of all, air is very rare. We are not even thinking about the cohesive force is greater or adhesive force is greater, because force between the water molecule or any liquid molecule and other liquid molecules would be cohesive force, and liquid and other air molecules would be adhesive force. Okay, but the density is so much here that the cohesive adhesive doesn't matter that much, so net force would be downwards. This thing is clear? Yes, no? Okay, see, consider a layer having thickness equal to what? The range of molecular attraction. Now if you consider any molecule within this layer, any molecule of liquid within this layer, so for this molecule, the number of molecules, number of liquid molecules in lower half of sphere of influence would be greater, much greater compared to the number of molecules in the upper half, and that's why net force on this molecule is also in downwards direction. Okay, and that's why now this layer, the topmost layer of the liquid, it is under some tension. Okay, see what kind of force will act on this molecule. If you consider a molecule over here, there will be net downwards force, okay, net downwards force, right, because of all other molecules, and also if you think of this molecule, it will get attracted from all sides um, by the molecules of liquid on the layer. Okay, exactly on the layer, right? It gets attracted on this side, this side, this side. So this layer is like a stretched membrane. Okay, this layer is like a stretched membrane. Okay, so this force per unit length is called as the surface tension, right? What is surface tension? So suppose this is liquid. Now you draw an imaginary line on the free surface of liquid. This is free surface of liquid. Then the force acting per unit length on that imaginary line, okay, it is known as the surface tension, right? So this layer, free surface of the liquid, it is like a stretched membrane, because if you consider, if you think of any molecule on that layer, it gets attracted from all sides due to other liquid molecules, okay, and therefore now, okay, so we define this quantity called as surface tension. It is the force acting per unit length of an imaginary line drawn on the free surface of liquid. So now you might have seen the insects crawling over the surface of water. So how can that happen? It's because of the weight of an insect. It is balanced. The weight of the insect is balanced by the force due to surface tension. Okay. So if you think of this line, if you draw a straight line on free surface of liquid, then force acting on that line would be like this. Okay. This line gets attracted from this side due to these liquid molecules, okay, and it gets attracted due to these liquid molecules on the other side. So now think of this insect, okay, it is crawling over the surface of water. What happens here is, so this membrane bends a little bit, okay, because of his weight, okay, its weight, and the surface tension, okay, now surface tension will act like this, okay. So if you resolve this surface tension along two components, there will be one vertical component, one horizontal component, okay. So the horizontal components of the surface tension or force due to surface tension, they get cancelled out, and the vertical components, as you can see, the vertical components will get added up, and therefore the net force due to the surface tension would be upwards. So which will balance weight of the insect, and that's why the insects can crawl over the surface of water or some liquids. Okay, this is clear, right? Okay, so after that, let's talk about the next concept, that is surface energy. Now what is the surface energy? So see, suppose I want to move this molecule A, okay, from this point to, let's say, this point inside the liquid. So now how much is the force acting on this molecule? So we have just seen that force acting on a liquid molecule which is inside the liquid, it is zero, okay. There is no net force acting on this molecule, because if you draw a sphere of influence, it gets attracted equally from all directions. So net force acting on this molecule is equal to zero. So if you move it anywhere inside the liquid, you don't need to do any work. It can move freely. So water molecules can move freely from here to there. Why? Because there is no net force acting on them, okay, and therefore you don't need to do any work, okay, because there is no force. So you don't need to apply any energy, any external force, okay, to move this molecule from here to here, right? You can move it from here to here, from here to here, here, but when it comes here at this point, now what will happen? So once it enters this layer, the topmost layer, having thickness equal to what? Having thickness equal to the surface, having thickness equal to the range of molecular attraction, okay. Having thickness equal to the range of molecular attraction, then what happens is, there is the surface tension acting on this molecule in downwards direction, okay. Force due to surface tension will act in downwards direction, right? So when this molecule enters this layer having thickness equal to the range of molecular attraction, there would be net force acting on this molecule in downwards direction due to other liquid molecules. Okay, so now in order to move it from here to here, you will need to do some work. Okay, in order to move it, let's say from here to here also, you will need to do some work because there is net downwards force due to other liquid molecules. So now therefore there would be an extra energy. Okay, if you want to move this molecule from here to here, you need to supply it some energy. So the molecules on the top surface, okay, or you can say in the top layer of the liquid, they have excess energy. Molecules at the free surface and up to the depth of range of molecular attraction, these molecules within this range, okay, within the layer of thickness is equal to range of molecular attraction, these molecules will have some extra energy, right? This is known as surface energy. Okay, so molecules at the top layer having thickness equal to what? Range of molecular attraction, these molecules of liquid will have some extra energy compared to molecules within the liquid, okay, in the interior of liquid. So this excess energy is known as surface energy. Okay, this thing is clear. So now we'll see the relation between surface energy and surface tension. Okay, so suppose this is a wire frame and it is dipped in a soap solution. Okay, this is a wire frame dipped in a soap solution, right? So a soap film will be formed on the wire frame, right? A soap film will be formed on the wire frame. Now here this wire, okay, wire CD, suppose it is freely movable, you can move this wire, right? So if you move it, what will happen? The soap film will expand. Okay, so if you move this wire like this soap film will expand, its free surface will increase. Okay, so now if you think of this wire, there is a force due to surface tension acting on this wire due to the soap molecules, and that force is in this direction. Okay, that force is in this direction, right? Okay, so you will need to apply some external force to counter this force and to increase its surface area. Okay, so now suppose increment in the surface area of soap film is dA. So dA would be equal to what? Suppose length of this film, length of this side, it is equal to L, and you are increasing, you are suppose stretching it by distance dx. So what will be the area? Increment in area, it will be equal to L times of dx, right? This length is L, this is dx, so increment in this area would be equal to L times of dx. Okay, okay, so as you see the soap film, it looks like it is very thin, right? Soap film is very thin, but still the soap film will have some thickness like this. If you see it through microscope, it will look something like this, right? And the thickness of the film, thickness of this film would be obviously greater than 10 raised to minus 9 meters. Okay, because you can see it, the thickness of this film would be greater than 10 raised to minus 9 meters. You cannot see up to, you cannot see the objects having length or size equal to 10 raised to minus 9 meter, right? So see, now there will be this one free surface and there would be one free surface on the other side. Okay, so now your wire, it is in contact with this free surface as well as that free surface. So if you are increasing the area of this surface will increase as well as area of that surface, the other surface, right? Surface facing the other side, that will also increase. Okay, and that's why the change in area would be equal to L times of dx on one side, L times of dx on the other side, and that's why the change in area would be 2 times of L dx. Is this thing clear, everyone? Okay, and therefore the work done, see, now let's talk about the work done in this process. So the area of the soap film on the wire frame is increased by dA. Suppose the work done would be equal to, see, you need to exert some force, okay, in this direction. So force is equal to what? The surface tension multiplied by length, right? Force is equal to what? Surface tension multiplied by length. Okay, we just saw that surface tension is equal to force upon length. So force is equal to what? Surface tension multiplied by length, T times L. But then as we discussed, there would be two surfaces. So force that you need to apply on one surface is T times L. On the surface at the back, it is also T times L. So the net force that you apply, it is T times of 2L, or 2 times of T times L, right? And therefore the work done would be equal to what? Force multiplied by displacement, that is F times dx, and force is T times 2L or 2 times TL, okay, and displacement is dx. So then therefore the work done is equal to this much, okay, right? And then see, this work done can be written as, okay, work done can be written as T multiplied by dA, because what is increment in surface area? So we have just seen that increment in surface area would be 2 times of L dx, okay. L dx is increment in surface area on one side, and on the other side also there would be same increment in surface area, therefore it is 2 times of L dx, okay. So this 2 times of L dx is equal to what? dA, okay, it's equal to change in surface area, and then this work done is stored as the energy of these molecules, okay, energy of the molecules within the free surface of liquid, okay, up to the layer of, you can say, the range of molecular attraction, okay. So let's say from now onwards the molecules on the free surface of liquid, okay, so it is implicit that the thickness of the free surface would be equal to a range of molecular attraction, okay. So these molecules have some extra energy, and this work done, or that energy, comes from this work done, okay, this is clear. So we are doing some, sorry, we are doing some work against the surface tension to increase this surface area. So that work done gets stored as energy of these molecules, okay, this work done gets stored as energy of these molecules at the free surface, and that is known as surface energy. So how much work we have done? It is equal to T times of dA, and therefore surface energy is equal to what? T times of dA, okay, surface tension multiplied by increment in the surface area, and therefore we get another definition for the surface tension from here, that is equal to what? The increment in energy, or the surface energy, you can say, divided by the increment in surface area, okay. So next let us discuss the angle of contact. Now what is the angle of contact? So now suppose you take a test tube and you pour some water in the test tube, okay, then you will see that the free surface of water makes some meniscus, water or any other liquid, you might have seen this in chemistry lab. So either it makes a concave meniscus like this, or it makes a convex meniscus, okay, it makes a concave meniscus or a convex meniscus, or it might be flat, right? So now see, this is, for an example, a kerosene oil, it will make a concave meniscus in the test tube, okay. Then this is mercury, it will make a convex meniscus, right? Okay, so what is the angle of contact? The angle of contact is the angle between the free surface of liquid, this is, can you see this free surface of liquid, and the solid surface at the point of contact. okay, measured inside the liquid surface. So from the surface of solid, okay, measured inside the liquid, okay. So this is known as the angle of contact, okay. So the angle between solid surface and free surface of liquid measured inside the liquid. This thing is clear? Yes, no? Okay, all right. Now let's see what's the reason of this angle of contact. So for an example, suppose this is some liquid and this is a solid surface, okay, this is some solid. You can take this example of a beaker, a glass beaker, and it contains some water, suppose, right? So now think of this molecule, think of this water molecule at the top, which is in contact with the solid surface or glass surface, you can say, okay. So now if you draw a sphere of influence for this one, then there are three kinds of molecules in that sphere of influence. One is the solid molecules, one is liquid molecules, and ones are the air molecules, right? There are three kinds of molecules: solid molecules, liquid molecules, and air molecules, right? So now what happens? So there would be some cohesive force, there would be some adhesive force, okay. So there would be the adhesive force between this water molecule or liquid molecule and the solid molecules, right? It will be directed like this. This is the adhesive force. Then there would be some cohesive force, okay, between this molecule and other molecules of liquid which come in this sphere of influence. So this is the cohesive force, okay. It will be directed like this, okay. So then see, what will be the net force acting on this molecule? So sum of this adhesive force and cohesive force, and also there would be some force due to the air molecules, but we are neglecting that force because again air is very rare, so we just neglect it, right? So there would be some little adhesive force due to air molecules also, you are neglecting that, okay. So now if you add it up, what happens is, suppose this is the resultant of these two forces, the adhesive force and the cohesive force. If it comes inside the solid surface, okay, the resultant is into the solid, then this angle of contact would be acute, right? Acute means smaller than 90 degrees. If the resultant force is inside of the solid, that means of course adhesive force is greater than the cohesive force, then the resultant force would be into the solid and angle of contact would be acute. So this angle would be smaller than 90, okay. Okay, so see, this free surface of liquid would be always perpendicular, as we discussed here also. If you think here, this is the free surface of liquid, okay, this is free surface of water, let's say. In what direction is the net force acting? It is downwards. What is the angle between the free surface and the net force? It is 90 degrees, okay. What's the angle between the free surface and the net force? It is 90 degrees. So here also you can think in same way. So this is the resultant force of the cohesive force and the adhesive force, cohesive force and adhesive force. Then what's the angle between, what should be the angle between the resultant of them and the free surface? It is 90 degrees, and because of that now the angle of contact becomes acute, okay. So if adhesive force is more, means what will happen? These liquid molecules, they tend to stick to the solid surface, right? So they will weight the solid surface, okay, because adhesive force is more. So they will leave the liquid molecules and they will cling on to the solid molecules, right? They will weight the solid molecules. This thing is clear. So if angle of contact is less, means that, so for that solid liquid pair, the solid can be, solid is wettable, you can say, okay, solid will get wet, if it is in contact with this liquid. Okay, so next you can come to here. So this is mercury, let's say. So the angle of contact would be obtuse, that means more than 90 degrees. So what happens here basically is there would be some adhesive force between. So if you think of the sphere of influence, there would be adhesive force between the mercury molecule and the solid surface. Okay, there would be some cohesive force between the mercury molecule and the other mercury molecules, and mercury molecules, they don't leave other mercury molecules that easily. So cohesive force is much more compared to that of adhesive force for most of the surfaces, okay, for most of the solids. And that's why mercury will not weight the solid if it is in contact with solid, because cohesive force is more. Okay, so other mercury molecules will not leave this mercury molecule that easily, right? So resultant of the adhesive and cohesive forces, it is inside of the mercury. And as we discussed, the free surface is perpendicular to the resultant force, right? Resultant force acting on this molecule. Okay, and then here the angle of contact would be obtuse, right? So now you need to remember 2-3 things here. So first thing, where would be the angle of contact obtuse or acute? So if cohesive force is more, the angle of contact would be obtuse. If adhesive force is more, the angle of contact would be acute, right? Cohesive force is more, then angle of contact would be obtuse. Adhesive force is more, angle of contact would be acute. Okay, then the free surface of liquid is always perpendicular to what? It is always perpendicular to the resultant of cohesive and adhesive forces. Okay, so the free surface is always perpendicular to them. And then third thing, if the angle of contact is acute, means of course the adhesive force is more, then the solid can get wet by the liquid, that liquid. Okay, and if angle of contact is obtuse, means the cohesive force is more, so solid cannot get wet by that liquid. Okay, is this thing clear, everyone? And we know that water can wet most of the surfaces. Okay, so for water the cohesive force would be much smaller compared to the adhesive force. Okay, and that's why this resultant force, so this is also an exaggerated diagram. So resultant force would be just like this. Okay, it will be well inside of the solid surface like this. And therefore now if you talk about the angle of contact here, the angle of contact would be very small, so it is almost zero. Okay, so if certain liquid completely wets the solid, means adhesive force is much more compared to what? That of the cohesive force, and that's why the angle of contact would be equal to what? Zero. Or you can say, if angle of contact is zero, then the liquid completely wets the solid. Okay, so this is true for pure water. So then this is a universal truth that every system in the universe tries to minimize the potential energy. Okay, every system in the universe tries to minimize the potential energy, right? Everything happens in that way. So for an example, if you think of gravity, okay, we shouldn't go to gravity, but still, now what happens? So suppose you think of these two masses, they are kept at infinite distance. Okay, then what happens is, so they come closer. So if they come closer to each other, the potential energy decreases. It is minus of gmm upon r, right? So why liquid is, or why drops of liquid, they are spherical? The reason behind that is the liquid wants to minimize the potential energy, and the sphere is a shape which will have least surface area, and least surface area means what? The least surface energy. Okay, so as we discussed, surface energy is what? Potential energy only, right? So if you want to increase the free surface, you will need to do some work against the surface tension. So if you are increasing the surface free surface, that means you are increasing the surface energy also. Okay, but if you leave this wire, no problem, I am explaining this. Okay, so if you take this example, suppose if you leave this wire as it is, what will happen? The soap film will shrink. Okay, by shrinking, what will it do? It will decrease its potential energy, right? Yes, no? Okay, so now the reason behind why the water molecules or any liquid molecules are spherical, the reason behind that is every system wants to decrease the potential energy, everything wants to minimize the potential energy, right? And the sphere is a shape where the surface area is minimum, and therefore surface energy, we know that surface energy is equal to what? T times dA, that means surface tension multiplied by the area, okay, surface area. And if surface area is minimum, then surface energy would be minimum, and that's why the drops are spherical. So sphere is such a shape where you can have minimum surface area, right, but maximum volume. Or you can say out of all shapes, all possible shapes in the universe, okay, sphere is such a shape where the surface area is minimum for the same amount of volume, you can say. Okay, you can take same volume of something, you can make a cube of it. Okay, you can make a sphere of it. So sphere will have least amount of surface in it, surface area, and that's why surface energy too. So this thing is clear why the liquid drops are spherical. Okay, after that, let's talk about the excess pressure across the free surface of a liquid. Okay, so see here. So now if you have a free surface like this flat free surface, then the pressure just above that surface and just below that surface would be equal, right? Pressure just above and just below would be equal. That's why the surface would be flat. If it is concave surface like this, if the meniscus is concave, then the pressure here on this side would be more compared to that of pressure on this side. Okay, so pressure at C would be more compared to that of pressure at D. And if you have convex surface like this, the pressure on this side would be more compared to that of pressure on this side. So this point is F, this point is E. So pressure at F would be more compared to that of pressure at E. Okay, let's remember this way only. So pressure outside is equal to pressure inside. Okay, so that's why you can say that this surface gets pushed equally from both sides, and that's why the surface would be flat. Okay, so for this surface you can say that pressure outside is more compared to that of pressure inside of liquid. So what will happen? So therefore it gets pushed more from outside. Okay, so that's why the concave surface is formed. Okay, because the pressure inside would be lesser, and here the surface is convex because pressure from inside is more compared to that of pressure from outside, right? This thing is clear, yes, no? Or suppose you have free surface of liquid, then pressure on the concave side is always more compared to pressure on the convex side. Okay, pressure on concave side is always more compared to that of pressure on the convex side. Okay, let's always remember it this way. Okay, so then now suppose I want to find out excess pressure inside a liquid drop, okay, and a bubble. So suppose this is my liquid drop. So for this liquid drop, what happens is, see, as we discussed, pressure on the concave side would be more compared to that of pressure on the convex side. Okay, so there would be some difference in pressure between inner side, okay, pressure inside of the drop and pressure outside of the drop. So pressure outside of the drop would be air pressure, right? So P in minus P out is equal to 2T divided by R. Okay, so this is liquid drop, let's say in air, or it might be inside some other liquid also. always the pressure inside minus pressure outside would be equal to 2T divided by R. So what is T? T is the surface tension. What is R? R is the radius of curvature of this surface. Okay, or suppose this is drop, then it is just radius of the drop. Okay, it is a drop, so it will be just radius of the drop, right? Now if you think of a bubble, then for a bubble there will be two surfaces, okay, two free surfaces. So here if you think of this is suppose a bubble, so there would be air over here, and suppose this is soap bubble, so there would be soap solution in this region. Okay, so then there would be pressure difference between this surface, okay, point inside and point over here, that will be 2T divided by R1. Then there would be pressure difference between this point and point outside, that would be 2T divided by R2. So what would be the net pressure difference between this point and this point? It will be 2T divided by R1 plus 2T divided by R2. Okay, 2T divided by R1 plus 2T divided by R2, right? And then if bubble is very thin, that means R1 is nearly equal to R2, then we can just say it is equal to R. So P in minus P out would be equal to 4T divided by R. Okay, if R1 is equal to, we can say R1 is equal to R2, then it is 4T divided by R. This thing is clear? Yes, no? We can see the derivation quickly. So suppose this is a liquid drop, right? And there is some pressure inside, that is P in, inside pressure, there is pressure outside, that is outside pressure. So now what would be the net pressure? That is pressure inside minus pressure outside. Okay, so that is net outwards pressure, right? So therefore force acting on this free surface, okay, free surface would be equal to what? This excess pressure, okay, excess pressure inside of the liquid drop multiplied by its surface area. Okay, so surface area is suppose A. So therefore now force is equal to what? Excess pressure multiplied by surface area, and suppose its radius increases by a very small amount, dr. Okay, so in order to increase this radius, you need to do some work against what? Force due to surface tension, and therefore work done in this expansion is equal to force multiplied by dr. Okay, work done in this expansion is force times dr. So force is P in minus P out multiplied by area. Area would be what? 4 pi r square, right? So work done is just equal to what? P in minus P out, inside pressure minus outside pressure, times area into dr, right? Then this work increases the surface potential energy. As we know, the work done against the surface tension increases what? Surface potential energy, and it is equal to T times dA. Okay, surface tension multiplied by area, and dA is what? Increment in the surface area. So then what is dA by dr? Okay, so this is quicker way of solving this. Suppose you take area is equal to what? It is equal to 4 pi r square. Okay, take its derivative with respect to the radius. So then d by dr of 4 pi r square, it's equal to what? 4 pi you can move outside, d by dr of r square, so that is equal to 2r, and dA by dr is therefore equal to what? 8 pi r. Okay, dA by dr is equal to 8 pi r. Then what is dA? So move dr on that side, so you get dA is equal to what? 8 pi r dr. Okay, dA is equal to 8 pi r dr. Okay, so substitute that in this equation. Okay, you substitute that in this equation, then what do you get? Okay, so work done is equal to T times dA, means work done is equal to what? T times of 8 pi r dr. Okay, and you found that work done is equal to what? P in minus P out multiplied by area into dr. Okay, so it is P in minus P out multiplied by area, which is 4 pi r square, times dr is equal to T times of 8 pi r dr. So then dr gets cancelled out. Then you have some simplification, like pi gets cancelled. Okay, this r square gets cancelled with this r. Then what remains here is r, because this 8 will get cancelled with 4. I mean 8 by 4 will give you 2 on this side. So what remains is 2T, and if you move that R on other side, so P in minus P out is equal to 2T divided by R. This thing is clear, everyone? Yes, no? Okay, but now nobody will ask you this derivation. So what you need to remember is P in minus P out means pressure difference between the inside and outside of a sphere. Okay, spherical drop is equal to 2T divided by R. And if it is a bubble, then what would be the pressure difference? It's equal to 4T by R if it is a thin bubble, and if a bubble has some thickness, that means inner and outer radius is different, then it is 2T by R1 plus 2T divided by R2. Okay, let us solve some problems based upon this. So this one is from NEET 2023. The amount of energy required to form a soap bubble of radius 2 cm from a soap solution is nearly. The surface tension of soap solution is 0.03 Newton per meter. Tell me. Anyone? So what would be the energy, or what would be the work done? Work done is just equal to T times dA. That means what? So initially there was no surface area. Now there is some surface area. So that is surface tension multiplied by 4 pi r square. Okay. But then see, this is a bubble. So bubble means there will be two free surfaces. So two free surfaces means you need to multiply this thing with 2. Right. Okay, this thing is clear. Yes, no? Okay, it's option C. Let us check. So you have 0.03 multiplied by 4, pi is 3.14, multiplied by r square is 2 square, so 2 centimeter square, so 2 into 10 raised to minus 2 square of that multiplied by 2. So then what do you get? This is 8, right? 2 square times 2 is 8, 8 times 4 is 32. Okay, so 0.03 is 3 into 10 raised to minus 2 times 32, okay, times 3.14, and you have multiplied by 10 raised to minus 4. So this is nearly, let's say 32 times 3.14 is nearly 100. 100 times this 3 into 10 raised to minus 2 is what? 300 into 10 raised to minus 2 means 3. 3 times 10 raised to minus 4, right? It's option C, correct. So this is simple, right? There is only one thing that we need to remember, that it's a soap bubble. So if it is a bubble, then we need to multiply by 2. Okay, because there will be two surfaces, two free surfaces, one inner free surface and one outer free surface. Right, this is clear. Yes, no? Okay, good. Let's see next one. If a soap bubble expands, the pressure inside the bubble increases, remains same, is equal to atmospheric pressure, decreases. Tell me. Now these are simple problems. If a soap bubble expands, the pressure inside the bubble, is it more, less?
Decreases.
Decreases, right? Because P in minus P out, okay, P in minus P out is equal to, this is a bubble, so 4T divided by R. Okay, so P out is the atmospheric pressure, that will remain same, right? So you can say P in is just equal to atmospheric pressure, let's say PA plus 4T by R. So if R increases, what will happen? This factor will decrease, atmospheric pressure will remain same, but this factor will decrease, right? So R increases means 4T by R will decrease, so pressure will decrease. Okay, this one is from 2020. right? And very simple one. Okay, let's see next one. A liquid does not weight solid surface if the angle of contact is, tell me, acute, obtuse, what?
Obtuse.
Should be obtuse, no? That means greater than 90 degrees, right? So again, very simple one from NEET 2020. Okay, all right. So this is yeah, is there any doubt in this? Anyone? No doubt, right? Okay, let's see next one. A soap bubble having radius of 1 mm is blown from a detergent solution having surface tension of 2.5 multiplied by 10 raised to minus 2 Newton per meter. The pressure inside the bubble equals point Z naught below the free surface of water. In the container, taking G equal to 10 meters per second square, density of water, okay, is 10 raised to 3 kg per meter cube. The volume of Z naught is, okay, a soap bubble having radius of 1 mm is blown from a detergent solution having surface tension of this much, right? The pressure inside the bubble equals at a point Z naught below the free surface of water in a container. Okay, so now these are two different things. You have a soap bubble, right? So then we know that pressure inside the soap bubble would be equal to what? Atmospheric pressure, PA plus 4T divided by R. Okay, this is pressure inside the soap bubble, and then it is equal to, they say, uh, pressure at a point Z naught below the free surface of water in a container. Okay, so pressure uh, inside a container at depth Z naught. Okay, this will be equal to what? There would be again some atmospheric pressure, right, plus rho g h, and h is equal to Z naught. Okay, so pressure here at point P, you can say it is equal to what? Atmospheric pressure plus rho g h, and h is equal to Z naught. Okay, Pa plus rho g Z naught. So this is pressure inside of a bubble. This is pressure at this point P, right? So this is 1, this is 2. Now both are equal, so you can equate these two. So if you equate these two, what will happen? The atmospheric pressure will get cancelled, and you have 4T divided by R equals to rho g Z naught. Okay, 4T upon R is equal to rho g Z naught, and then we want to find out the density of what do we want to find out? The distance of that point Z naught, right? So you can take this rho g on the other side, and therefore Z naught will be equal to what? It is 4T divided by R rho g. Put the values. Okay, so it is equal to 4 times of what is surface tension, 2.5 multiplied by 10 raised to minus 2 divided by R. R is 1 mm, 1 into 10 raised to minus 3. Rho is uh, it is what? Water only, so rho is 10 raised to 3, of course. Okay, and G is 10. So if we solve this, what do we get? 10 raised to 3 minus 3, this thing gets cancelled out. Okay, then this 10, okay, 4 times 2.5 is 10, 10, 10 gets cancelled, 10 raised to minus 2. So 10 raised to minus 2 meters means 1 centimeter. Okay, Is it correct? Check my calculation. Yes, no? Alright, so then it is option D, right? Alright, let's see next one. A rectangular film of liquid is extended from this area to this area. If the work done is equal to this much, the value of surface tension of the liquid is, tell me. Again, this is very simple, right? So let's say initial area is A1, okay, final area is A2, okay. Therefore, work done is equal to what? T multiplied by dA, that is T multiplied by 2 times of A2 minus A1, okay. What is A1 and A2? It is area of one side, okay. Let's remember this, it is area of one side only, I mean 4 times 2 or 5 times 4. This is area on one side only, and because this is a film, again there will be two free surfaces, right? So therefore work done is equal to T times dA, so 2 times A2 minus A1, this is change in area, and then you want surface tension, so move that on other side, so you get surface tension is equal to work divided by 2 times of A2 minus A1, then put the values. So work done is 3 multiplied by 10 raised to minus 4 joules divided by 2. A2 is 5 times 4, and this is centimeter times centimeter, means if you convert it to meter, 10 raised to minus 2 and 10 raised to minus 2, 10 raised to minus 4. So 5 times 4 multiplied by 10 raised to minus 4 minus 4 times 2 into 10 raised to minus 4. You can take the 10 raised to minus 4 common. So this is 20, 20 minus 8 is 12. 12 times, okay, let's keep it 12. So 12 by 3 is 4, 4 times 2 is 8. So now this is equal to 1 by 8 multiplied by numerator you have 10 raised to minus 4, in denominator also you have 10 raised to minus 4, that gets cancelled. So 1 by 8 means 1 by 4 is 0.25, 1 by 8 is 0.25 divided by 2, so 0.125, right? 25 divided by 2 is 12.5, okay. So that is the answer, it's option B, I guess. Right, this one is clear, yes, no? Okay, this is simple, right? Let's see next one. The spherical drop, the radius of spherical drop of water is 1 mm. If the surface tension of water be this much, 70 into 10 raised to minus 3 Newton per meter, the pressure difference inside and outside of drop will be, okay, tell me. This is very straightforward, the pressure difference inside and outside, okay. So P in minus P out, so you just need to check whether it is a drop or a bubble. So it's a drop, that means 2T divided by R, okay. Pressure difference inside and outside is 2T divided by R, so that is 2 times of the surface tension, 70 multiplied by 10 raised to minus 3 divided by R, R is 1 mm, so 1 into 10 raised to minus 3, 10 raised to minus 3, it gets cancelled out, 70 times 2, 140, that is the answer. Alright, let's see next one. What should be the pressure inside a small air bubble of 0.1 mm radius situated just below the water surface, okay. So tell me. So this is water surface, suppose, and it will be flat, okay. This is your air bubble, so on outside there is water and inside of this bubble there is air. What will be pressure difference here and Okay, the question is, what should be pressure over here inside of this bubble? Tell me. Here the pressure difference, will it be 2T upon R or 4T upon R? Everyone, will it be 2T by R or 4T divided by R? Forty by R. Okay, Yamini, Salvakumar. Okay, no problem. See, this is an air bubble. Okay, air bubble, and there is water outside, right? So how many free surfaces are there? 1, 2, only one surface, right? If it is a soap bubble, there is air inside, air outside, and in between there is a layer of soap or soap film, you can say. So there is one free surface here and one free surface here, but this is an air bubble inside water. Okay, air bubble inside water. So there is air here and water here, so only one free surface, right? Yes, no? Okay, so only one free surface means the pressure difference would be 2T divided by R, right? Only one free surface means pressure difference would be 2T upon R. And then what would be pressure difference or pressure here? So this is pressure at this point, you can say it is equal to the atmospheric pressure. Okay, pressure just below that would be also equal to the atmospheric pressure, right? And our bubble, okay, what should be the pressure inside a small air bubble, okay, which is situated just below the water surface. It is just below the water surface, means pressure here and here would be just equal. That means it is air pressure. So pressure inside is just greater by amount of 2T by R. Okay, so we have P in minus P out. To simplify this, so I can say this is like a air drop, okay, inside water. Okay, surrounding is water and this is air drop inside, right? Yes, no? It's like that. Okay, because for water droplet or water drop, you can say the medium inside is complete water, medium outside is air. Okay, so this is similar to that, just interchange the medium. Okay, this is air bubble inside water. You can think of it because it has got only one free surface. Okay, so P in minus P out would be just equal to what? 2T by R, and P out is equal to atmospheric pressure. So you move it on the other side. So P in is equal to P out, which is atmospheric pressure, plus 2T by R. Then you put the values. It is 1.013 multiplied by 10 raised to 5. This is given. Okay, and roughly we should remember that atmospheric pressure is equal to 1 into 10 raised to 5 if it is not given. Okay, all right. So normal atmospheric pressure is 1 into 10 raised to 5. Then you have 2T by R, so it is 2 times of T. T is 7.2 multiplied by 10 raised to minus 2, and R is 0.1, right? 0.1 mm. 0.1 multiplied by 10 raised to minus 3. So let's make this 1.013 into 10 raised to 5. Let's keep it like that. Actually options are not close, so we can approximate it to 1 also, no problem. This is 7.2 times 2, 14.4. 14.4 multiplied by 10 raised to minus 2, and in denominator minus 4, that means will be 14.4 multiplied by 10 raised to minus 2. Right? So 14.4 into 10 raised to minus 2. Am I correct, or this? Okay, it will not change much actually. So it should be, it can't be 2 into 10 raised to 5. So it will be option C, I guess. Okay, so let's do this calculation. 2 times 7.2 multiplied by 10 raised to minus 2, that is 14.4 into 10 raised to minus 2. That's correct. And 0.1 multiplied by 10 raised to minus 3, right, because R is that much. Okay, so that is 10 into, oh, 10 raised to minus 4 in denominator will become, oh, it is 10 raised to 2. Sorry. It's 10 raised to 2. Okay. So then, now I want to make this power same, power equal, then only I will be able to add it up. So it is 1.013 multiplied by 10 raised to 5 plus this will be 0.014 multiplied by 10 raised to 5, 0.0144, right? Then you can add it up. So this 1 3 and 1 4, it will give you 27274. Okay, so the answer would be equal to 1.0274 into 10 raised to 5. Okay, so yeah, that is option C. Right, this one is clear? Yes, no? Okay, good. Did somebody calculate it earlier? You must have calculated, right? All right. Okay, then let's see next one. A liquid drop of radius r breaks into 64 tiny drops, each of radius r. If the surface tension of the liquid is T, then the gain in energy is, tell me. A liquid drop of radius r. Okay, so for big drop, radius is equal to what? R, radius of big drop. Okay, radius of big drop is equal to r, and for small drop it is, let's say, equal to small r. It's given actually. For radius of small drop, it's equal to r, and then the surface tension is also given. Then gain in energy is, so this drop breaks into 64 tiny drops. Okay, now we had discussed this thing. What will happen if a drop breaks into n number of tiny drops? What will happen? The volume will remain same. What will happen to the volume? Volume will remain same, but the surface area would increase. Okay, surface area would increase. So let's find out how much does it increase, and then we know that energy d is equal to what? Just t times of change in surface area. Okay, so whatever is increment in surface area, you need to put it over here, and you will get increment in the surface energy, gain in surface energy, right? So we can say volume of big drop, it is 4 by 3 pi r cube, and let's calculate it for general case. It's equal to n times of 4 by 3 pi small r cube. Okay, 4 by 3 pi, 4 by 3 pi gets cancelled out, and therefore you get r cube is equal to n times of small r cube. Okay, and therefore r is equal to n raised to 1 by 3 times of r, taking cube root on both sides. So I think we had calculated this earlier, right? So r is equal to n raised to 1 by 3 times small r. Okay, so then you want change in surface area. So change in surface area dA is equal to, it is n times of final surface area of one drop, okay, n times of surface area of one small drop, okay, that is 4 pi r square minus surface area of one big drop, right? Initially it was only one big drop, that is 4 pi r square, okay, drop is spherical, that's why the surface area is 4 pi r square. So it is n times of, now you can take this thing on other side. So what will happen, you can move this thing on other side, so it will be, because small r will be equal to what, n raised to minus 1 by 3 times capital R, capital R, okay, or we can substitute this thing also, no problem. So it is n times of 4 pi r square minus 4 pi multiplied by this capital R is n raised to 1/3 of small r, so n raised to 2/3, we have square of that, that's why it will be n raised to 2/3 of small r, okay. Some options are in terms of capital R, some are in terms of small r, so we need to solve this, okay. So then you can take 4 pi r square common, right, 4 pi r square common, okay. So what remains is 4 pi r square multiplied by n minus n raised to 2 by 3, okay, n minus n raised to 2 by 3. This thing is clear, everyone? Okay, then you can put the value of n. So what is that? So therefore it is equal to 4 pi r square multiplied by 64 minus 64 raised to 2 by 3. So take cube root of 64 and then take its square. What is cube root of 64? 4, okay, and square of that is 16. So 64 minus 16, how much is it? 46? No, 48, sorry, 48, 4 pi r square, okay, 4 pi r square, 48 multiplied by 4 pi r square. So is there such an option? 48 times 4 will give you what? 192. 192 multiplied by r square into t, right? So this is dA, okay, and therefore dE is just equal to what? 192 multiplied by t into 4 pi, r square, pi r square, sorry, 192 t multiplied by pi r square. So that is option D, right? So we just got lucky. Is this thing clear? Yes, no? Okay, we got lucky in the sense that our answer was in terms of small r, and there is correct option is also in terms of small r. If it is not in terms of small r, then we need to solve it. Okay, we need to convert it in terms of capital R, right? Okay, so the thing to be remembered here is this thing, that capital R is n raised to 1 by 3 times of small r. Whatever is n, n here is 64. Okay, we could just substitute the value also here, right? But capital R is n raised to 1 by 3 times small r. And then depending upon whether the drop is breaking or whether new drops are, I mean drop is breaking and n number of drops are formed, whether n drops coalesce to form a bigger drop. Depending upon that, we can find out the change in area. Okay, so if a drop breaks and n drops are formed, then final area would be greater than the initial area, and if drops combine, if they coalesce to form a bigger drop, then there would be decrement in any area, and in that case what will happen, some energy would be released because surface energy will decrease. Okay, so in that case the energy is released in the form of heat. Okay, this thing is clear, everyone? Okay, let's see next one. A water drop is divided into 8 equal droplets. The pressure difference between the inner and outer side of the big drop will be, tell me. So once again, a big drop has radius big R, capital R, and it's equal to n raised to 1 by 3 times of small r. Okay, so that is equal to, you have 8 drops now, so it is 8 raised to 1 by 3 times small r, means 2 times of small r. This is capital R. Okay, and then the pressure difference between inner and outer side of the big drop. So if radius increases, what happens to the pressure? P in minus P out. For a drop it is 2T divided by R. R increases, R has become twice, right? Radius of big drop is 2 times of radius of small drop, and the question is, okay, what is the pressure difference between inside and outside of big drop only? So for big drop, radius is twice as that of what? Smaller drop, and that's why pressure would be half. Okay, so this is simple. Let's see this one. A certain number of spherical drops of a liquid of radius small r coalesce to form a single drop of radius capital R and volume V. Okay, a certain number of spherical drops of a liquid of radius small r coalesce to form a single drop of radius capital R and volume V. If T is the surface tension of the liquid, then tell me. Then we need to find out the energy, whether it is released, absorbed. Okay, first of all, what's happening? Certain number of spherical drops of liquid coalesce. Coalesce means what will happen, as we discussed just now, that coalesce means surface area would decrease. Surface area decreases means surface energy also decreases. That means some amount of energy is released. Okay, but then it is there in two options. Okay, option A also, option C also. That means we will need to solve. Okay, right. So then how much is the amount of energy released? So E is equal to T times of dA, T times of change in surface area. Okay, then T times of what is change in surface area? So n drops are, they coalesce, right? So final surface area would be equal to what? It would be equal to, suppose, 4 pi r square. Initial surface area would be equal to n times of 4 pi small r square. Okay, so let's put that here. So in one option it is 1 by r minus and this one. Okay, all right, so it is equal to what? So initial surface area n times of 4 pi r square minus final surface area, which is 4 pi r square, and then we need to put what do we need to do here? Okay, the volume is also given, and in all of the options volume is there. That means somehow we need to adjust volume here, right? Somehow we'll need to adjust the volume. So what would be volume? Volume would be same, right? So volume of n small drops is n times of 4 by 3 pi r cube, okay, that will be equal to volume of one big drop. So that is equal to 4 by 3 pi capital R cube, okay. So as we can see in the options, there is volume, it's taken common, so we need to adjust the volume over here. So how do we do that? So for that we'll need to multiply and divide by 4 by 3 r here, okay. So let me just write the volume. So it is n multiplied by 4 by 3 pi r cube, right. So n times of 4 pi r square was already there. So n times of 4 pi r square was there. That means I have multiplied by 1 r and I have divided by 3. So this thing multiplied by 3 by 4, 3 by r will remain there, right. And here also it is 4 pi r square. I want to adjust volume, so it will be 4 by 3 pi r cube. So I have multiplied by r by 3, so I need to divide by that, so therefore 3 by r. And then we'll take volume common, so this thing is volume, right, this thing is also volume, okay. Volume would be equal, right, volume of n small drops is equal to volume of one big drop. So then we can move this thing as a volume outside, okay. And 3 also we can take common, so this is volume, 3 also we can take common. So what remains is 3 times of volume into T, and then 1 by r from first term and 1 by capital R from the second term. So 1 by small r minus 1 by capital R. This is the energy, okay. So it is option C. This thing is clear, everyone? Yes, no? Right. Okay, good. So this is from 2014. Let's see next one. The wettability of a surface by liquid depends primarily on density, angle of contact between the surface and the liquid, viscosity, surface tension. Tell me. It depends on the angle of contact, right. It's option B, okay. So whether the liquid will wet the solid surface, we can determine from the angle of contact, okay. Let's see next one. Liquid does not wet the solid surface if the angle of contact is, tell me. We just saw this, right. It is greater than 90, okay. It's option D, okay. Okay, good. Let's see next one. Capillary tube. Okay, so first of all we need to understand the capillary rise. This is based on capillary. Let's see this one. Assertion: sometimes insect can walk on water. Reason: the gravitational force on insect is balanced by force due to surface tension. So is it correct? Tell me. We saw this at the beginning only. Insects can walk on the water. Reason behind that. Have you seen insects walking on water? We have seen this at the beginning only. Okay, you might not have seen, but insects do walk on water, okay. All right, so answer is both A and R are correct, and R is correct explanation for A, okay. So see here. So this is an insect walking on surface of water. So here what happens is there is this stretched membrane. Okay, the free surface of water is like a stretched membrane. So now because of the weight of this insect, what happened, in it bends. Okay, the free surface, it is like a stretched membrane, and because of the weight of this insect, it will bend like this. Okay, it bends like this, and because of that, now the force due to surface tension will act like this. Okay, on this side it is always along the free surface of the liquid, and here it acts like this. Okay, so if you resolve this force due to surface tension along two components, one horizontal component and vertical component, horizontal component and vertical component, so you can see horizontal components get cancelled out and vertical components get added up. They are in vertically upwards direction and they balance the weight of the insect. Okay, and that's why the insects don't sink, they can walk. Okay, right? Can human beings walk? Of course not, because our weight is much more. It cannot be balanced by surface tension. All right, so then, okay, see this one also. Water drops take spherical shape when falling freely. Then this is assertion. Reason is water has minimum surface tension among all liquids. So is A correct or is B correct? I mean, is assertion correct or is the reason correct? Assertion is water drops take spherical shape when falling freely. Reason is water has minimum surface tension among all liquids. So this is definitely not correct. Okay, water doesn't have minimum surface tension. Right. Water drops take spherical shape when falling freely. This one is correct. Yes, no. So its answer should be A is correct. Oh, it should be opposite to this one. Option D. A is correct and B is incorrect. There is no such option. I think its answer should be A is correct and B is incorrect. Okay, in fact, surface tension of water is much higher. All right, so yeah, this is the answer. A is correct. Okay, not only water, anything, any liquid mostly will take spherical shape when it is falling, and actually it's the other way. If surface tension is more, okay, if surface tension is more, then what will happen, uh, it will be more spherical shape, you can say, because liquid molecules will, surface tension is more means what, the force, the cohesive force between the liquid molecules is more. Yes, no. Okay, so it should be other way. Water has minimum tension is definitely incorrect. Water has huge surface tension. Okay, so the answer to this one is A is correct and B is incorrect. Okay, this thing is clear. Yes, no, everyone. right? Okay, so this is option E. There is no such option, so let's include one. This is option E. All right. So next, let's talk about the capillarity. So now what is capillarity? So what is capillarity? The phenomenon of rise or fall of a liquid in a capillary tube. Okay, it is called as capillarity. So this is the capillary tube, and it has got very small radius, okay, of the order of few mm. So now the formula for this rise or fall of the liquid is given by H is equal to 2 times T cos theta divided by R rho g. Okay, so now the terms are very clear, right? So H is the height, that means rise or fall. Okay, H can be positive, H can be negative. Okay, so it is equal to 2 times T. T is the surface tension of the liquid, then multiplied by cos of theta. So theta is angle of contact. Okay, so when you dip this capillary tube in any fluid, any liquid, then there will be some meniscus. Okay, the meniscus, it might be concave or convex, right? So there would be certain angle of contact. Okay, so if that angle of contact is acute, then this theta, cos of theta would be what? Positive. If it is obtuse, it would be negative. Okay, and that's why H would be positive or negative depending upon that, divided by R rho g. So rho is of course the density of this liquid, and R is the radius of the capillary tube. R is what? The radius of the capillary tube, right? This thing is clear. We need to remember this formula. Okay, so then now let's talk about this capillary action. How does this happen? Okay, so suppose this is the capillary tube. Now we have zoomed it. Okay, and this is some liquid, let's say water. Okay, so this is meniscus of water. So there is water in the capillary tube, right? So now angle of contact here would be what? It is acute. Okay, so suppose this is some liquid, not water. For water it would be 0 degrees, but here it is acute, suppose. Okay, so for an example, kerosene, right? So then what happens? So see here, now if you consider a molecule of solid, solid means the capillary tube, it is made up of glass. The liquid will be in contact with the solid along the circumference. Okay, because this is circular, cross sectional area of capillary tube is circular, that's why the liquid will be in contact with the solid along that circle, you can say. Okay, circumference of the circle, right? So then if you consider, let's say this point, that means this molecule of the solid, okay, or glass, then the force due to surface tension acting on that, it is in this direction. Okay, if you consider this molecule of the solid, then force due to surface tension acting on it would be in this direction, right? So now see, liquid exerts some force on solid. Okay, liquid exerts some force on solid molecules because of the surface tension, and therefore you can say that solid will also exert equal and opposite force. Okay, so if this is the force due to the surface tension of the liquid, then this is force due to the capillary tube. Okay, F suffix C is the force due to the capillary tube, right? This is again the force due to capillary tube. And now you can resolve this force due to the capillary tube along two components. So what we have taken is, see, the capillary tube will have cross section like this. We have considered the end points, okay, these two end points. So force on this one, okay, so suppose there is some liquid molecule over here, so force on that one will be in this direction, force on this one, it will be in this direction. So force due to the capillary tube, it is in this direction, force on this molecule, it is in this direction, and that one we resolve along two components. Okay, so this force we are resolving along two components. So you can see that, so one vertical component, one horizontal component, and here one horizontal component, one vertical component. So what happens to the horizontal components is, horizontal components are equal and opposite, so they get cancelled out, and only vertical components will get added up, and that's why the net force on this liquid which is forming a concave meniscus inside the capillary tube, it is vertically upwards. And that's why what will happen? Since the net force is vertically upwards, the water level or this liquid level, it will rise up in the capillary tube. Okay. So this rise is called as capillary action. This thing is clear? Yes, no? Okay. Similarly, here now there is a convex meniscus. So for an example, mercury. Okay. So suppose there is mercury inside the capillary tube, it forms a convex meniscus. Therefore, now if you consider molecules of capillary tube, then force on this molecule, okay, due to mercury, due to the surface tension of mercury, it will be in this direction. Force on this molecule of solid, it will be in this direction. Okay, force due to the surface tension. Then the solid also, that means the capillary tube also exerts equal and opposite force, but that will be in this direction now. Okay, so for this, okay, for this force due to the liquid, the force due to the capillary would be in this direction. For this force, the force due to capillary, it would be in this direction. Again, you can resolve this force due to the capillary along two components. So one is horizontal component, one is vertical component, one is horizontal component, one is vertical component. So the horizontal forces, they get cancelled out. Okay, so if you consider this capillary tube, right, so there would be some liquid over here. Okay, so now the liquid which is in contact with the capillary tube, the horizontal component of forces acting on that would be like this. They will be acting like this. Okay, equal and opposite, equal and opposite, equal and opposite everywhere. But the vertical components are vertically upwards only. So they all, sorry, here in this case they are vertically downwards only. So they all get added up. They all get added up, and that's why the net force would be in downwards direction. So level of the liquid will fall down if it forms a convex meniscus. Okay. So if a liquid forms concave meniscus inside capillary tube, its level will increase. Okay, it will rise up. And if it makes a convex meniscus, its level will fall down. This thing is clear, everyone? Yes, no? Right. Okay. So then now see, suppose here the level of the liquid goes up. Okay, the level of the liquid, it goes up. So see here, now suppose R is the radius of the meniscus. Okay, it's not radius of the tube, it is radius of the meniscus. What does that mean? So suppose you have this meniscus like this. Okay, R is radius of that meniscus, right? So this is part of some circle, you can say. Okay, suppose you have a concave meniscus like this, it is part of some circle. Okay, so radius of this circle is suppose small r, right? Radius of this circle is suppose small r. Okay, now we are going to understand the formula for rise or fall. Okay, so r is radius of the meniscus. Then now see here, so suppose this liquid level rises up. Okay, so here what you can say is, consider this beaker and this is the capillary tube. Okay, there is liquid, any liquid, let's say kerosene inside this glass beaker, okay, this container. So we know from the Pascal's law that if it is a flat surface, if free surface of liquid is flat, then pressure just above it is equal to pressure just below it, right? And pressure at same height would be equal. Yes, no? Pressure at the same height would be equal, right? So pressure at this point and pressure at this point would be equal. Okay, because here if you consider point in the interior, then here what will happen? The free surface would be flat. But then now here you consider suppose capillary tube is just dipped in. So now suppose the liquid level here, it goes up. Okay, so liquid level here goes up. Okay, then now the meniscus at the top would be what? It would be again the concave meniscus only. So pressure at this point C and pressure at the point D, this is the relation between them, everyone. Okay, so we had studied this, that suppose there is a concave, suppose free surface of liquid is concave, then the pressure difference between the concave side and the convex side, okay, the point on the concave side and point on the convex side. Suppose point C is the point on concave side, D is point on the convex side. So PC minus PD is equal to what? 2 times the surface tension divided by R. R is what? Radius of meniscus. It's not radius of the capillary tube. Okay, this thing is important. Then you move this, see, PD on this side and 2T by R on the other side. So we get PD is equal to pressure at the point D is equal to what? PC minus 2T by R. Okay, pressure at this point is equal to what? PC minus 2T by R, right? And then now here the pressure at all points. So if this is some liquid, then pressure at all points at the same height should be equal, right? Pressure at all points should be equal. So pressure over here, okay, pressure over here, it would be equal to pressure at point A. Pressure at B would be equal to pressure at A. This thing is clear? Yes, no? Right? And then how much is the pressure difference between point D and point A? How much is the pressure difference between point D and point A? It would be equal to rho GH, right? So pressure at point A would be equal to pressure at point D plus rho GH. Okay, and what is pressure at point D? So it is pressure at point C, okay, minus 2T by R plus rho GH. Okay, and then now pressure at point E, you can say, is equal to pressure at point B, and it should be equal to pressure at point C, because all of them are what? They are the atmospheric pressures. Okay, yes, no? Right? So pressure at point A is also what? The atmospheric pressure. Okay, pressure at point A, it is also equal to atmospheric pressure, and pressure at point C is also equal to the atmospheric pressure. Okay, therefore you can just cancel it out, and what do you get then is minus 2T by R is just equal to rho GH. Okay, minus 2T by R is just equal to rho GH, right? Or rho GH is equal to 2T by R, and then we wanted to find out H. So what we can do is we can just move rho G on the other side, but then see, this is radius of the meniscus, and suppose capital R is the radius of the capillary tube. So then there is relation between these two radii. Okay, so see, this is the meniscus, its radius is small r. Okay, and the angle between this surface, free surface of liquid, and the solid surface, it is called as angle of contact. So this angle is equal to what? This angle is equal to theta. Okay, then now this is angle of contact. Okay, and that means this line is along what? It is tangential to the free surface of liquid, and then if r is the radius of meniscus, then we know angle between the radius and tangent is equal to what? It is 90 degrees. So this angle is equal to 90 degrees, and therefore if this is theta and this much angle, this much total angle is equal to 90 degrees, okay, then how much would be this angle? This would be 90 minus theta, right? And if this is 90 minus theta, because this angle is also 90 degrees, no? So this angle is theta, this would be 90 minus theta. If this is 90 minus theta, then this angle has to be equal to theta. Okay, and if this is theta, then you can see in this triangle, what is the relation between this capital R and small r? So cos of theta would be equal to what? Capital R divided by small r. Okay, cos of theta would be equal to capital R divided by small r, right? And therefore, what would be capital R? It would be r cos theta. Okay, capital R is equal to small r cos theta, or if I want small r, it would be small r, then take the small r on other side, take cos theta on this side. So small r would be equal to capital R divided by cos theta. And what is theta? Theta is the angle of contact. Is this thing clear, everyone? Yes, no? Okay, because then we are going to substitute it. So when you substitute that here, small r is equal to what? Capital R divided by cos theta. So then what do you get is 2t divided by capital R divided by cos theta, and that cos theta goes to the numerator because it is in denominator of denominator, right? So then you get rho g h is equal to 2t cos theta upon r. Okay, then you wanted h, so you can take this rho g on other side. So you get h is equal to 2t cos theta divided by r rho g. But this r, capital R, it is what? It is the radius of capillary tube. Small r is what? Small r is the radius of meniscus. Okay. So we need to remember this formula, and we need to also remember that radius of meniscus, small r is equal to what? It is capital R divided by cos of theta. Okay, is there any confusion in this? Right, good. So why is there rise or fall in the liquid level in capillary tube? It is because of force due to surface tension. Now this is one way of deriving this expression. There is another way also. So another way is kind of simple. Okay, I mean it's similar. So what you can say is, so see here, the weight of this liquid column, okay, weight of the liquid column is equal to what? You can say weight of the liquid column is equal to mg. Okay, so what would be weight of liquid column? It is equal to mg, which is mass can be written as density times volume. Okay, so rho multiplied by what? Volume of this cylinder. It would be equal to what? Pi r square h, right? Volume of the cylinder is pi r square h. Then you have multiplied by g. Okay, so this is the weight, and it is balanced by force due to the surface tension. Right, this thing is clear? Yes, no? Or shall I explain that? So let me explain it in different way also. So if you can relate with that thing, or the, I mean, both ways are identical. So see this one. So the liquid level rises up because of what? Because of the force due to surface tension, right? Liquid level rises up because of the force due to surface tension. So see here, this angle is theta, it is angle of contact, okay, and the forces would be equal and opposite, right? So this angle is also equal to theta, okay. So now suppose I want to resolve this force along two components. So what would be those two components? So two components would be, this would be fc cos theta, and this would be fc sin theta, right? Because this is angle theta through the angle cos component, away from angle sin component, right? Then now first of all, what would be the force due to surface tension? So force due to surface tension in magnitude, okay, force due to surface tension in magnitude, it is equal to what? Surface tension multiplied by the length at which it is acting. So how much is the length? So it is 2 pi r, right? Surface tension multiplied by 2 pi r. So this is force due to surface tension, right, in magnitude. And So Fc would be equal and opposite, right? Fc would be equal and opposite. Okay, so Fc is also equal to force due to surface tension. This is according to Newton's third law, and that is T multiplied by 2 pi r, right? And then the vertical component of this force due to the capillary tube is, it balances the weight. Okay, so vertical component of Fc balances the weight of liquid column, right? Balances the weight of liquid column. So therefore you have vertical component would be what? Fc cos theta, right? So Fc cos theta is equal to weight of liquid column, it's equal to mg. And what is m? Mass is density into volume, so it is density multiplied by, what is volume? Volume of the cylinder, right? This liquid column would be cylindrical, so it is pi r square times h, you can say. Okay, multiplied by, you have acceleration due to gravity. And what is Fc? So Fc is t into 2 pi r, so t times 2 pi r times cos of theta is equal to, see, you get rho into pi r square h into g, and there are some cancellations, so pi will get cancelled out. Okay, what else gets cancelled out? This r gets cancelled out with this one. Oh, I wrote different r at two places. What will be this r? It is radius of the capillary tube, right? So this force due to surface tension, it is acting on along the radius of capillary tube, not radius, circumference of capillary tube. So our r would be what? Radius of the capillary tube, right? So this r will also get cancelled out, and therefore what do you get is, ultimately you will get the same thing. H is equal to, see, this r gets cancelled out with square, pi gets cancelled out. Okay, so what remains here along with h? R, rho and g. You move it on other side, so you get 2t cos theta divided by r rho g. Okay, the same formula, 2t cos of theta divided by r rho g. Okay, so we need to remember this formula, right? This thing is clear, everyone? Yes, no? Okay, all right, good. Then now let's see the last point, that is effect of various things on the surface tension. Okay, so now due to the increment in temperature, what will happen? Surface tension will increase or decrease? Surface tension will decrease. The reason behind that is, see, molecules of the liquid, where does the surface tension come from? It comes from the cohesive force between the molecules of a liquid, right? Surface tension comes from cohesive force between the molecules of a liquid. Okay, so now if temperature increases, what will happen? The density will decrease, because molecules, they will vibrate. Okay, because energy of molecules is increasing, they will vibrate and they will go away from each other. So density of liquid will decrease. So density of liquid decreases means what? There will be less number of molecules in this sphere of influence compared to the earlier case. That means when the temperature was low, okay, there were more number of molecules because density of liquid was more. Now if the temperature increases, density decreases. That's why there will be less number of molecules in the sphere of influence, and that's why you can say that any molecule will get attracted with a lesser force, so surface tension will decrease, right? Is this thing clear? Yes, no? Okay, the next is I'm sorry, effect of impurity. Okay, effect of impurity. So now there are various kinds of impurities. If the impurity is insoluble or sparingly soluble, then the surface tension decreases. Okay, if impurity is insoluble, for an example, you take water, then suppose there is something that is not soluble in water. Okay, any example? Uh, Something insoluble in water. Soap is soluble, salt is soluble, sugar is soluble. Okay, water is universal solvent. So we need to change it, right? Okay, so change the liquid, right? Suppose you take some oil. Okay, suppose you take some oil and you dip some salt in the oil, right? So chances are that it will be insoluble. Okay, so if it is insoluble, sparingly soluble means slightly soluble. Okay, then the surface tension would decrease. Surface tension in that case would decrease. It is insoluble means what? Okay, so here that concept comes that when solid, um, the adhesive force between solid and liquid is more, then what happens? Solid gets wet. Okay, so similarly, if adhesive force is more, then your any impurity, okay, whatever you add in a liquid, it will get dissolved. Right? Yes, no. This thing is clear. Okay, in order to get this molecule mixed, yeah, so we had seen yesterday that if adhesive force is more, then what happens? Then liquid molecules leave other liquid molecules and they stick to the solid molecules. Okay, they go closer to the solid molecules, right? So here also you can say if adhesive force is more, then the solid molecules and liquid molecules, they will get mixed well. Okay, the liquid molecules will enter. Suppose there are n number of solid molecules, you are adding this impurity. If adhesive force is more, then other liquid molecules can enter in between the solid molecules and it will get dissolved. Okay, so if impurity is soluble means the adhesive force is more compared to what? That of the cohesive force. So this impurity, it acts as if it is part of the liquid only. Okay, and it gives rise to increment in surface tension, right? But if it is not soluble, means what will happen? The adhesive force is less. Okay, and therefore it cannot become part of the liquid, so surface tension is decreasing. Because if you consider sphere of influence, okay, surface tension is decreasing means force of attraction between a molecule and other molecules in surrounding is decreasing. Okay, that's why surface tension would decrease. This thing is clear to everyone, right? So we need to remember only this thing, that if the impurity is insoluble or sparingly soluble, then the surface tension decreases. If the impurity is completely soluble, then the surface tension increases. Okay, all right. So this is effect of impurity and the temperature on the surface tension. Okay, so then let's see some problems based upon this thing. So let's see this one. A capillary tube of radius small r is immersed in water and water rises in it to height h. Now here small r itself is the radius of capillary tube. Okay, the mass of the water in the capillary is 5 grams. The mass of water in capillary is 5 grams. Then another capillary tube of radius 2r. So first is having radius r, another one has radius, let's say r dash equals to 2r, right? It is immersed in water. The mass of water that will rise in this tube is. So this is the question. Okay, tell me. Okay, first of all, let's start with the formula of rise of liquid in the capillary tube, the height of liquid. Okay, so this is water. So formula is what 2t cos theta divided by, now I will write small r only because they are saying that small r is the radius of capillary tube. So divided by r rho g. Okay, this is the formula, right? And now suppose some liquid rises up in the capillary tube. So this is the liquid in the capillary tube. So this liquid will have some mass. Okay. So now in first case, radius of this tube is r. So mass was 5 kg, not 5 kg, 5 grams. Then the radius becomes 2r. So what will be the mass? This is the question. So we know that mass is directly proportional to what? Volume. Okay, mass is directly proportional to volume. So this liquid will have some volume. Okay, so mass is proportional to the volume because mass is density times volume. Okay, or let me write mass is equal to density times volume. So density is constant. Okay, so mass is equal to rho multiplied by what is this thing? Volume. Volume of the cylindrical column. Okay, volume of liquid column. So that is pi r square times h, right? And then here you can write for h, what is h? H is 2t cos theta divided by r rho g, and it is water. For water, theta is equal to 0. So you can just say that h is 2t divided by r rho g because cos of 0 is 1. Okay, so then this rho will get cancelled out. Okay, then r and this thing will get cancelled out. Okay, here in numerator you have r square, in denominator you have r. So square gets cancelled out with r and only r remains. And now we just want that thing. So here see, mass would be directly proportional to r. So if mass is directly proportional to r, so if radius is r, mass of the liquid column is 5 grams. If radius becomes 2r, then what would be the mass? 10 grams, right? Because mass is directly proportional to r. So m dash would be equal to what? So you can say m dash upon m is equal to what? R dash divided by r, and that is 2r upon r. R gets cancelled, so you have 2. Take mass on other side, so m dash is equal to 2 times m. M prime is equal to 2 times m. So that is 10 grams. Right? Is this thing clear? Everyone? Okay, good. So then we can just remember mass of the liquid column is directly proportional to radius of the capillary tube. Okay. All right. Let's see next one. So this was from NEET 2020. Let's see next one. 3 liquids of densities rho 1, rho 2 and rho 3 with rho 1 is greater than rho 2 is greater than rho 3 having the same value of surface tension T rise to the same height in 3 identical capillaries. Okay, capillaries are identical, right? Liquid is different. Okay, 3 different liquids, rho 1, rho 2 and rho 3 are the densities, and the angles of contact theta 1, theta 2 and theta 3 obey. They obey what? Okay, tell me. All right. So 0 would be of course less than or equal to one of them, right? So either it is option A or option B, and C and D is not possible because minimum angle of contact is not pi by 2, right? Minimum angle of contact is 0. So C and D is not possible. Then we need to check which ones are greater, either the theta 1 is greater or theta 2 is greater, right? So that we need to check. Okay, so heights are same, that means h1 is equal to h2 is equal to h3, okay, and their surface tension is same, okay, surface tension of these three liquids is same. So you can write 2t cos of theta 1 divided by r rho 1 g, right, r rho 1 g is equal to 2t cos theta 2 divided by r rho 2 g, and it's equal to 2t cos theta 3 divided by r rho 3 g. Okay, then you can cancel out this 2t by r, or first of all we could just say that height is equal to what, 2t cos theta upon r rho g. So what is same in those three? So t is same, right, r is same, so that's why we can just get rid of that. Okay, and we could just write that cos theta 1 upon rho 1 is equal to cos of theta 2 divided by rho 2, and it is equal to cos of theta 3 divided by rho 3. But then you have this relation that rho 1 is greater than rho 2 is greater than rho 3. So if denominator is greater, that means numerator has to be greater, then only the ratio would be same, right? Right? If this ratio is same, that means if denominator rho 1 is greater compared to rho 2, that means cos theta 1 must be greater than cos of theta 2. Okay, yes, no? Right. So therefore I can say, since rho 1 is greater than rho 2 is greater than rho 3, therefore cos theta 1, okay, cos theta 1 must be greater than cos of theta 2 must be greater than cos of theta 3. And then you know that cos is maximum for angle equal to 0, and if angle goes on increasing up to pi by 2, let's say, what happens? The value of cos goes on decreasing. Cos of pi by 2 is 0. So if cos, the value of cos is more, okay, cosine of an angle is more, that means angle has to be small, right? Because cos 0 is maximum, cos of pi by 2 is minimum, cos of pi by 2 is 0. Okay, in magnitude, right? In the magnitude, cos 0 is maximum, cos of pi by 2 is 0. This thing is clear? Yes, no? Okay, why pi by 2? Because see, why are we not considering angles more than pi by 2? Because if angles are lesser than pi by 2, then only the liquid will rise, and they say that heights of the liquid columns are equal. That means they are all positive or all negative. Okay, either all positive or all negative. This thing is clear, everyone? If you take obtuse angle, then what would be the height? It would be positive or negative. Liquid will rise or fall. It will fall. Okay, so that's why we are taking maximum angle to be pi by 2, right? So then if angle is small, cos of an angle is more, that means theta 1 must be less than theta 2 must be less than theta 3. Okay, so it is option B. Theta 1 is less than theta 2 is less than theta 3, and all of them are lesser than pi by 2. Okay, so this has to be the case. Is this thing clear, everyone? Okay, good. Let's see next one. Water rises to a height h in capillary tube if length of capillary tube above the surface of water is made less than h, then okay, so what is the question? Water rises to a height h in capillary tube. If length of capillary tube above the surface of water is made less than h, then what will happen? Water rises up to a point a little below the top and stays there. Water does not rise at all. Water rises up to the tip of capillary tube and then starts overflowing like a fountain, and water rises up to the top of capillary tube and stays there without overflowing. Tell me what will happen? So we have h is equal to what for water? 2t cos of theta divided by r rho g. Okay, h is equal to 2t cos of theta divided by r rho g. Okay. Yes, what will happen? What do you think will happen? So the question is, see, you have this capillary tube and water can rise up to this level, let's say. Okay, suppose the water can rise up to this level and this was original level. So this is the height of water in the capillary tube. Okay, so then what you do is you cut this capillary tube over here. Then what would happen? So option C, it will overflow like a fountain. Okay, option D, option D. Okay, everyone is saying option D now. Why is it option D? Okay, so see, actually what happens is, it would be option D, that's correct. Water rises up to the top of capillary tube and it will stay there without overflowing. So reason behind that is, see here, what we can say, h is equal to 2t cos of theta divided by r rho g, and it can be written as what? 2 times of t divided by small r rho g. And remember, what is small r? So small r is the radius of the meniscus, right? It is radius of the meniscus. Okay, if meniscus is like this, let's say this is the radius. Okay, so then now what happens is, suppose you cut this tube. Okay, suppose this is a cut tube. Okay, earlier the height was suppose up to this one. Now the water level rises up till this height, or let's say, let me draw another tube. So this is another tube which is cut. Okay, and then this is the original water level, and suppose the water rises up to this level. So how much is angle of contact for water? So it is 0 degrees, right? Or let's take very acute angle. So suppose water rises up to this height, let's say up to this height, then angle of contact would be like this. Okay, it is 0. Okay, suppose it rises like this, then what will happen? Water will keep on rising. Okay, so here if you consider the radius of the curvature over here, okay, if the angle of contact is something small angle, then there would be some radius. Okay, so here this radius is just equal to what? Because angle of contact is 0, so here you can say radius of this meniscus just equal to what? The radius of the capillary tube, because theta is equal to 0. So cos 0 is equal to 1, right? Then now this water will start, the level of water will start going up still, and here what will happen then? So as this level goes up, then the shape of meniscus will change. Okay, so in order to overflow, first this level has to rise, right? You agree with that? Then as this level rises up, what will happen? The shape of the meniscus will change, and therefore the radius of curvature, it gets adjusted in a such a way that h becomes just equal to the maximum available height only. Okay, so this r gets adjusted. That means shape of the meniscus, which was meniscus was like flat only earlier, because angle of contact is what? It is 0. So shape of meniscus will change. It will become concave, then less concave, less concave, like this. So earlier it was like this, not flat. Earlier it was like this. Okay, because angle of contact is 0. Then it becomes less concave, less concave, less concave, because water level is rising, and then ultimately it will become flat. But then the shape has changed in such a way that what happens? The h and r becomes, they get adjusted in such a way that the maximum available height is what? The height which comes out of this formula. Is this thing clear? Yes, no? So r gets adjusted in such a way that the height of the liquid column becomes equal to the available height only. It does not overflow. Is it clear? Yes, no? So in order to overflow, water has to rise up first. Okay, the level of water has to increase first. So the shape of meniscus, which was like this, it becomes less and less and less concave, and ultimately it becomes flat. So that this r changes, r is the radius of meniscus, it changes, okay, in such a way that the available height only becomes what? The maximum height up to which the water can rise. Okay, and it does not overflow. Okay, if meniscus remains the same, why will not meniscus remain same? It's because, see, why is it like this, the meniscus in first place? Why is it like this? Because there is some capillary tube above this water level, right? So meniscus can be like this. Okay, it can be like this here. Why it can be like this? Because there is some capillary tube above the water level. But when the water level rises up, okay, so see, you are pulling down the capillary tube. So capillary tube is pulling, not you, water is pulling down the capillary tube. So capillary tube pulls up the water, okay, according to Newton's third law. So this goes on happening, but here now there is no capillary tube above the water, you can say that, and that's why now there is no capillary tube. So what will pull the water up? Okay, is it clear? Yes, no? Everyone? Right. So this question has been repeated, and answer to this is what? It rises up to the top of capillary tube only, right? Sometimes they give you numbers. The height of water in the capillary tube is suppose 18 centimeters or something like that, and there is some other capillary tube. Okay, so when it is dipped in water, the height above the water surface, it is just water level, it is just suppose 5 centimeters. Then what will happen? Again, the water will rise up to 5 centimeters, and then it will start overflowing. That is one option. One option is it will just go to the 5 centimeter height and it will stay there. Okay, so that would be the answer. Why is it so? The shape of meniscus will change in such a way that it adjusts the height or rise of the column to only the available height. Okay, so that is the answer, right? So please remember this. Okay, then let's see next one. So a 20 centimeter long capillary tube is dipped in water. the water rises up to 8 centimeter. If the entire arrangement is put in a freely falling elevator, this is a similar question, the length of water column in the capillary tube will be. See here. Now, suppose you have this capillary tube, okay, and water can rise up to 20 centimeter. So water rises up to 8 centimeter. It's given the earlier height is 8 centimeters. It goes till this height, suppose this is 8 centimeters. Okay, this original height is 8 centimeters, and then you have h is equal to what? H is equal to 2t cos of theta divided by r rho g, this formula. Now here, if you keep it in an elevator, okay, and it is freely falling, then what will be g? So let's say g prime is the value of g, and it is equal to what? G minus a, g minus the acceleration. Okay, we studied this in mechanics, right? Suppose there is freely falling elevator, okay, then the weight experienced is what? M times g prime, it is equal to m times g minus a. That means the value of acceleration due to gravity felt over there would be equal to what? G minus a. Yes, no, this thing is clear? Everyone? Do you remember this formula? Okay. If the lift goes up, then what would be the weight? Mg prime, and that is equal to what? M times g plus a. Okay. If lift goes down, then what would be the weight? It is m times g minus a. Okay, of course, it is going up or down with some acceleration. Okay. So in one case there would be plus a, in one case there would be minus a. So when it falls down, what is the weight? It is m times g minus a. But here it is freely falling, means how much is a? So a is equal to acceleration due to gravity. So g dash is equal to what? 0. G prime is equal to 0 because a is equal to g. Okay. So this is given, a is equal to g because lift is freely falling. So g prime is equal to 0, and therefore now what should happen in principle? So if g prime is 0, then h would become what? Infinity. But fortunately they have not given infinity, right? If g becomes 0, then what would be the value of h? It will become infinity. Okay, but they have not given infinity here. Okay, so what would be the answer? So again, it doesn't go to infinity. Okay, it just goes to the whatever height is available and stays there. This is the answer, right? It doesn't go beyond the available height because shape of the meniscus will change in such a way that the maximum rise would be just equal to what? Maximum rise would be just equal to the available height. Okay, so the answer to this is also just available height, and it is 20 centimeters. All right, so you have this capillary tube. So now it is freely falling. Okay, okay, no problem. So you have a capillary tube which is freely falling, right? So now, do you remember this formula that what would be g prime, the value of acceleration due to gravity, okay, felt by an observer who is freely falling? So if you remember, for an example, take this elevator. This is suppose this is an elevator and there is person inside the elevator, right? Then now if elevator is steady, the lift is steady, then there are two forces acting on the person. One is the force due to gravity, which is mg, and one is the normal reaction. So what is weight felt by the person? N is just equal to mg in this case. But if the lift accelerates upwards, net force is equal to mg, right, in this case. So now suppose lift is moving up with acceleration a, then what can we say? That F is the net force. It must be equal to what? It must be equal to N minus mg, the upward force minus downward force. Therefore N is equal to F plus mg in this case. Okay, and what is F? F is mass times acceleration. Okay, and plus you have mg, so you can take m common, so it is m times g plus a. Okay, m times g plus a is the normal reaction. Then this is the weight experienced by the person, so you can write this thing as weight is equal to what? Mass multiplied by, what is this thing, mass multiplied by g prime. So g prime in this case will come out to be equal to what? If lift is accelerating upwards, g prime would be equal to g plus a. If lift is accelerating downwards, then in that case g prime would be equal to g minus a, right? So in this case, what is happening? Your lift, capillary tube is dipped in water and it is kept in a falling elevator. It's freely falling. That means what would be the acceleration? Acceleration would be equal to g, and then g prime is equal to what? G minus a, right? And a is equal to g. So what would be the value of g prime there? G prime would be equal to just 0. Okay, so because g prime is equal to 0, the maximum possible height can be what? It can be infinity. But then the water cannot rise up to infinity. What happens is it rises up to the maximum available height, and then at that height what happens? The shape of meniscus changes in such a way that even if you use this formula, then what will happen? Shape of meniscus changes, okay, in such a way that this maximum height just become or maximum rise in the liquid column, it just becomes equal to the maximum available height. This thing is clear? Okay, everyone. So this is just similar to the last problem. This is another version of the same problem. Welcome. No problem. All right. So same problem asked in different way. Okay. All right. So here there is no problem because infinity is not given. But if they give infinity also, then still what would be the answer? Whatever is the maximum available height, that's the answer. Okay. All right. Let's see next one. Assertion: the water rises higher in a capillary tube of small diameter than the capillary tube of large diameter. Reason: height through which the liquid rises in the capillary tube is inversely proportional to diameter of capillary tube. Okay, so is it correct? Yes, no? Let's write h is equal to what? 2t cos theta divided by r rho g. So h is inversely proportional to r, right? So assertion is correct, reason is also correct. Yes, no? So what is the answer? Option A. Okay, this thing is clear.